The flow of air in a rectangular channel with an inlet, an outlet and a cylindrical obstacle is calculated in this fluid analysis tutorial. The analysis results show the velocity vector, the velocity gradient contours and the streamlines inside the channel. A new project is created first. Create a new project. Click the File tab and select New Project. Set up the analysis space as follows. Set Model Unit Millimeter. Set Analysis Space 3D. Click OK button. The initial setting has been done. A central part of flow path, inlet, and outlet are created. On the Model tab, click Solid and select Box Specify Length on the submenu. Designate the start point. In the Parameter Input dialog box, enter start point x0, y0, z0, and click Next button. Set the width. Enter width 100 and click Next button. Set the depth. Enter depth 100 and click Next button. Set the height. Enter height 50 and click Complete button. A central part of the flow path has been created. Create another box. In the Parameter Input dialog box, enter start point x15, y-20, z15 and click Next button. Set the width. Enter width 20 and click Next button. Set the depth. Enter depth 20 and click Next button. Set the height. Enter height 20 and click Complete button. The inlet box has been created. Create another box. In the Parameter Input dialog box, enter start point x100, y65, z15 and click Next button. Set the width. Enter width 20 and click Next button. Set the depth. Enter depth 20 and click Next button. Set the height. Enter height 20 and click Complete button. The outlet box has been created. Click Exit button and exit from the dialog box. Flow path bodies must be united to one in the fluid analysis. Unite three flow paths, boxes. On the Model tab, click Unite Boolean. On the modeling window, select all bodies by using Area Selection function with mouse. Click Complete button in the Unite Boolean dialog box. Three flow paths, boxes, have been created. Next, draw the cylinder body of the obstacle. On the Model tab, click Solid Body and select Cylinder, Solid Body in submenu. Designate the center. In the Parameter Input dialog box, enter center, x25, y75, z0 and click Next button. Specify the radius. Enter radius 10 in the Parameter dialog box and click Next button. Specify the height. Enter height 50 in the Parameter Input dialog box and click Complete button. Click Exit button in the Parameter Input dialog box and exit. The obstacle, cylinder, has been created. We set the analysis conditions. On the Model tab, click Analysis Condition. The Analysis Condition Setting dialog will show up. Select Fluid Analysis Bernoulli on the Solver tab. Go to the Fluid Analysis tab. Confirm that analysis type is set to steady-state analysis and laminar flow/turbulent flow is set to turbulent flow, and click OK button. The analysis conditions have been set. Set the body attributes and material properties for the bodies of the flow path. Highlight the flow path body and click to select on the modeling window. On the right-click menu, click Body Attribute/Material Property. In the Body Attribute/Material Property Setting dialog box, enter Body Attribute Name, Flow Path. Select 01_fluid on Material DB and select 000_air. Then click OK button. Click on the cylinder on the modeling window. On the right-click menu, click Body Attribute/Material Property. In the Body Attribute/Material Property Setting dialog box, enter Body Attribute Name, column. Select 02_metal on the Material DB and select Material Name, 007_Fe and click. Click Edit Data button of Material Property. In the Edit Material Property 007_Fe dialog box, confirm that state Solid is selected on the Solid/Fluid tab and click OK button. If state Solid is selected, the body is treated as an obstacle. Then click OK button in the Body Attribute/Material Property Setting dialog box and exit. On the Model tab, click Paint Bodies. The bodies will be painted according to their attributes automatically. The body attributes and the material properties have been set. Set the boundary conditions. Forced inflow, flow velocity, and natural outflow are set to inlet and outlet respectively. On the Model tab, click Select Face on the drop-down list at Switch Object pull-down. Highlight the inlet surface and click to select. On the right-click menu, click Boundary Condition. In the Boundary Condition dialog box, enter Boundary Condition Name, Inlet, and click Edit Data button. In the Edit Boundary Condition dialog box, apply settings so that the flow velocity becomes 1 meter per second. On the Fluid tab, select Boundary Condition Type, Inlet. Confirm that Inlet Type, specify flow velocity is selected. Enter 1 meter per second and click OK button. Then click OK button to exit the Boundary Condition dialog box. Then, highlight the outlet surface and click to select. On the right-click menu, click Boundary Condition. In the Boundary Condition dialog box, enter Boundary Condition Name, Outlet, and click Edit Data button. In the Edit Boundary Condition dialog box, confirm that on the Fluid tab, Outlet is selected as the boundary condition type. Natural outflow is selected for the outlet type. Click OK button. The boundary conditions have been set. Now, set the mesh size and run the solver. On the Model tab, click Analysis Condition. The Analysis Condition Setting dialog box will show up. Click the Mesh tab. Deselect Set the General Mesh Size automatically. Enter 6 in General Mesh Size. Click OK button. On the Model tab, click Run Mesher/Solver. The calculation will start. Please wait a moment while the analysis calculation is finished. The Calculation Finished dialog box will show up when the calculation finishes. Select both fields and tables and click Show button. The calculated value table will show up. The calculation results are available in various formats. The calculated value table shows the flow rate on the wall face, the wall force that the obstacle receives from the fluid, and the pressure loss caused by the flow of fluid from the inlet to the outlet. Close the table and the screen will change to Results window, and the meshing result will show up. We take a look at the gradation contour of the flow velocity. On the Results tab, click Gradation Contour. The gradation contour diagram of the flow velocity will be shown. Let's take a look at the results at the cross-section. On the Results tab, click Show Cross-Section. The cross-section dialog box will show up. In the cross-section dialog box, select Simple Mode. Click XY Plane. Click Create button and Close button in order. The cross-section will show up. We can see how the incoming air flows toward the outlet after hitting the obstacle. Show the vectors of the flow velocity. On the Results tab, click Element Vector. The vector diagram of the flow velocity will show up. Let's take a look at the results at the streamlines. On the Results tab, click Show Cross-Section to cancel the display of cross-section. Click Element Vector to cancel the display of vector diagram. Click Streamlines. The streamlines will be displayed. Finally, save the project. Click the File tab and select Save Project As. Enter the file name and the location in the Save As dialog box, and save it. Saving allows you to launch Femtet at a later date, open the project, and review the model and analysis results. That's it for the fluid analysis tutorial video. See the tutorial topics in the Femtet help for more information. Thank you for watching until the end.